So we've got false method mixtures in this problem. It's a little bit more complicated than it looks. The problem is you take a lump of ice, so we'll make it 0.1 kilograms, but it's at -10 degrees C. So it's straight out of the freezer, and you're dropping it into some water. We're not even going to worry about the container. We're just going to say we've got 0.5 kilograms, and our water is a warm day. It's been sitting outside and it's at 30 degrees C. And we're just popping the ice in there. And all we're asking is what is the temperature of the two once they reach thermal equilibrium. Once the ice melts, what will this combination be in terms of temperature? And it's actually, it looks relatively simple. It's actually a little bit trickier because of the change of state. Because first the ice has to warm up to 0 degrees C, and then it's got to melt. And both of those processes are going to take energy from the water to do that. So we've got this warming up, melting, and then our method of mixtures after that to see what temperature the two finish at. And just to make things a little more awkward as well, specific heat capacity of ice is different from the specific heat capacity of water. So specific capacity of ice is 2,100 joules per kilogram per degree Kelvin. And we've got to worry about the latent heat of fusion as well. Remember, it doesn't matter if the ice is melting or the water is freezing. It's the same process. So it's the same amount of energy. It's just, in this instance, the ice is melting, so it's gaining energy. But if we were freezing it, it would be losing the same amount of energy per kilogram. So that's joules per kilogram. So that's the latent energy of fusion of ice. And then, of course, to finish off with, we've got the old 4,200 joules per kilogram per degree Kelvin specific heat capacity of water as well. Okay, so the first thing we're worried about is this ice warming up, going from 10 to 0. So what energy is required for that? Well, it's C ice delta theta. So that's going to be 0.1 times by specific capacity of ice, 2,100, times by the temperature increase. It's going up 10 degrees. Oh, we've got a 0.1 and a 10, so they're just going to cancel out straight away. So 2,100 joules is absorbed by the ice as it gets to 0. It's still ice, hasn't changed state yet, but it's warmed up. So then it needs to melt. And the energy for this is the mass times the latent heat of fusion, latent energy fusion. So that's going to be the mass again, 0.1 times by the 3.3 times 10 to the 4. So that's going to be 3.3 times 10 to the 3, or 3,300 joules. Okay, so those two added together, it's going to be 5,400 joules. So that is how much energy the ice absorbs to get to blue water. And that's how much energy the water loses to the ice. Okay, so what temperature is our hot drink by the time the ice is melted? Well, that's going to be the energy going water again is mass specific capacity of water times by the change in temperature. So we've got 0.5 kilograms of water times by 4,200 times by delta. So the change in temperature. Well, we know this. It's 5,400 joules. So it's going to be, so the change in temperature is going to be 5,400. To be fair, again, we should really put it as minus 5,400, because that's how much energy it's lost, divided by the mass is 0.5, and that's 4,000 times by 4,200, and that will come to minus 2.57 degrees C. So our water has cooled down 2.57, and this isn't our final solution. This is just how much the water in the glass has dropped as the ice has melted. Okay, so our temperature of our water in the glass is 30 degrees. Take away that, so our water in the glass is now 27.43 degrees C. Okay, so that's so now what we've got is some water at 0 degrees C. And we've got 0.1 grams of that, 0.1 kilograms of that, and we've also got 0.5 kilograms of water. What do we say it was? 27.43 degrees C. Now those two are mixed together in a glass. Now we do our method of mixtures to say what will those two finally result. What will be the thermal equilibrium when those two mix together? So CW. Oh, and we'll need to say actually the temperature. Let's call the temperature they settle at to be θ1. So for our cold little bit of melted ice, we're going to have the mass times by specific capacity of water times by the temperature it ends up at. Take away what it's starting at 0, will equal the mass of the water times by specific heat capacity. So let's call that what was. That was what was the mass of the ice, that's the mass of the water, times by the change in temperature here to 7.43, take away θ1. So that's our water was no longer at 30 degrees because the ice has melted in there. This is now the change in temperature as the 0 degrees C, 0.1 kilogram of water mixes with our warm water. Okay, so what have we got? Well, we can cancel those straight away. Okay, so we've just got 0.1 times θ1, and that's 0.1 times 0 is 0, so that's going to be on that side. Here we've got 0.5 times 27.43, take away 0.5 θ1. So that's just multiplying out of those brackets. If we add 0.5 θ1 on both sides, then we get 0.6 θ1 equals these two multiplied comes to 13.715. So θ1 is going to be 13.715 divided by 0.6 equals 22.86 degrees C. Is that a reasonable value? You've got a glass of water that's 30 degrees. You've got half a kilogram of that, and you put 1 kilogram of ice in, and it cools it down slightly. Yes, that looks reasonable. Okay, but you can see that the awkwardness of the problem is actually you've got to take the ice from -10 up to 0. That's going to take some energy out of the warm water, and then the ice has got to melt, and that's going to take some energy out of the warm water before you get to this point where you're using actually the method of mixtures to find out what the final result is. Okay.